Two different beakers of water. One is hot, one is cold. I'm going to add some food coloring to each one. See if you can determine, just by looking, which is the hot and which is the cold. The one on the left is hot water. The one on the right is cold. Cold, hot. Why the difference? Why the difference in the behavior of the food color? Our title is Kinetic Molecular Theory. What we think of as temperature is really an index of random motion of molecules that make up the substance. The higher the temperature of the matter, the more energetic the molecules are. We saw that. In the cold water, the food coloring didn't move around very much because the water molecules weren't moving around very much, so they weren't bumping them around too much. But in the warm water, the hot water, molecules of water in the hot water were moving much, much faster, much more energetic. They bumped those food color molecules around fast, rapidly, and able to get them to mix homogeneously throughout that solution very quickly. Okay, so temperature. Higher the temperature, the more energetic the molecules. Now let's get a little more quantitative than simply that. Okay, so temperature and kinetic energy are actually related to one another. And kinetic energy, here's our formula, 1/2 mass times velocity squared. So keep it in mind, people, that it is 1/2 times mass times velocity squared. Okay, so we square the velocity before we do the rest of these things. So in terms of kinetic energy, velocity of the particle, how fast it's moving, has a lot more to do with its kinetic energy than mass, but mass cannot be left out. And so 1/2 mv squared. What is m? M is mass. And what is v? V is velocity. Essentially the speed of the molecules. The Kelvin temperature of a sample is directly proportional to the average kinetic energy of the molecules. And when I say average, I mean average. If we have a sample and we take the Kelvin temperature of that, that's the average kinetic energy of the molecules. Now keep it in mind that not all the molecules are moving at exactly the same. Not all the molecules have exactly the same kinetic energy in that sample, but it's all pretty close. There's always going to be some strays, though. Okay, so temperature measures the average kinetic energy of the molecules that make up a substance. So if we're talking about gases, then temperature measures the average kinetic energy of the molecules of that gas, because we're relating all of this to gas right now. Now, another piece of information that is important in terms of describing behaviors of gases is pressure. So where is pressure really coming from? Well, gas pressure is caused by the collision of gas particles with a surface. And we'll talk about this more in class, but when we're talking about gas pressure, that's what we're talking about. That is what's causing gas pressure, is the collision of gas particles with either the inside surface of the container, if we're talking about the pressure of the gas within, or if we're talking about the pressure on the outside of a container, we're talking about the collision of the outside gas molecules with the outside surface of the container. Atmospheric pressure, air pressure, is pressing on us, of course, from the outside. And where does that come from? The collision of all the air molecules with us. So really, these two things right here. Kinetic molecular theory is really this, but we've got to have this part as well in order to talk about pressure. So kinetic molecular theory provides the explanation for the observed behavior of gases. So what we're going to do in our next set of notes is we're going to talk about all the gas laws, and we're going to explain them in terms of kinetic molecular theory. Why are we seeing the mathematical relationships that we're seeing? All right, now there's one thing I feel like I need to talk to you guys about average kinetic energy that is really, really important. So let's say we have two gases. Let's say we have a sample of oxygen gas and we have a sample of helium gas. And both of those gases are at the same temperature. Okay, if those two gases are at the same temperature, that means that they have the same average kinetic energy. So, same temp, same temperature means same average kinetic energy. Are the molecules of those gases moving at the same speed? They're at the same temperature. They have the same average kinetic energy. Are their velocities the same? No, their velocities are not the same. Why? Remember, kinetic energy is 1/2 mv squared. We have to take mass into account. So, because oxygen is a more massive molecule, it has a greater molar mass, its particles are moving slower than the particles of helium. So, two gas samples, they're at the same temperature. That means they have the same average kinetic energy. The oxygen molecules have a slower velocity than the helium molecules. Okay? Greater mass means they're going to have slightly lower speed. So let's make this really easy. Let's say the kinetic energy was 4. Okay, and I'm just going to make two numbers here to make it really, really simple. Okay, if this mass is 2 times what is 4? 2 times 2. Okay, velocity would be 2. Helium, smaller molar mass. So let's say its mass is 1. Remember, I'm simplifying, way simplifying. If its mass is 1, 1 times what is 4? 4, right? So its velocity is greater. Smaller molar mass, same kinetic energy, same temperature. Okay? All right, that's it.